This is a crash course on dynamic optimization for economists, so I put particular emphasis on economic applications and not so much on mathematical details and proofs. The lecture consists of 3 parts and 3 different videos. The first one deals with the preliminaries, so differential equations and difference equations and how to solve simple forms of them. The second part deals with discrete time dynamic optimization, first by means of the method of Lagrange, where we discuss the advantages and disadvantages of this simple approach, and then we move on to the approach by Hamilton-Jacobi-Bellman. And the third part deals with dynamic optimization in continuous time by means of Pontryagins maximum principle. There are many nice textbook treatments of these topics, in particular the following 3 I can recommend. The one by Dixit, Optimization in Economic Theory. The one by Darren Asimoglu, Introduction to Modern Economic Growth, also has 2 chapters on dynamic optimization. And for German speakers, the book by Feichtinger and Hartl, Optimale Kontrolle ökonomischer Prozesse, Anwendungen des Maximumprinzips in den Wirtschaftswissenschaften. Before we start to go into the details of dynamic optimization in parts 2 and 3 of this crash course, we discuss the preliminaries here in part 1. And we really start with the most basic concepts, and we then move on step by step and build on this knowledge that we have accumulated. Now, the most fundamental point is how we conceptualize time. And there are 2 ways of conceptualizing time. One is that we can think of time evolving continuously. So that means that we do not experience gaps between different points in time, and that's somehow also how we experience time in the real world. However, there is a second concept, namely that we could think of time evolving discretely, and that might be better suited to situations when we have discrete time points at which we measure certain variables. So in reality, particularly with respect to macroeconomic data, we don't measure variables in a continuous way. We measure them on a yearly basis or on a quarterly basis. For some variables, we have data on a weekly basis, such as unemployment, but we don't have it on an even higher basis usually. So from this point of view, it might make sense to conceptualize time in a discrete manner. Now, the interesting thing is that the mathematical methods how to solve the problems in continuous time versus discrete time, they differ quite a bit, because in continuous time, as we will see in a moment, we can differentiate a variable that is measured in continuous time with respect to time, which we cannot do in discrete time. However, despite the fact that the mathematical methods differ quite a bit, the outcome, the final results, they are remarkably similar in terms of interpretation. And that's the good thing. So a priori, it's often not really clear whether we should use continuous time or discrete time frameworks, and it very much depends on the judgment of the researcher who analyzes a certain problem, which method he might find more appropriate in this particular context. And sometimes continuous time frameworks lead to an easier treatment of a certain problem, and sometimes it's discrete time that allows for the solution to be obtained in an easy way. Sometimes it also helps, if you get stuck in solving a certain problem, that you switch the time formulation, and often that helps and you can move forward with the other time formulation. Now, the main difference from a mathematical point of view between the 2 time concepts is that a variable measured in continuous time is differentiable with respect to time, and the variable that is measured in discrete time is not differentiable with respect to time. We see this easily in these 2 diagrams. The first one depicts a variable that is measured in continuous time, and the second one a variable that is measured in discrete time. Actually, it's the same series. And we see that in the first diagram the function is continuous, there are no gaps, and therefore the derivative with respect to time can be calculated. In the second diagram, we see there are gaps. The function is not continuous, and this would have been necessary for the function to be differentiable with respect to time. So we also see the difference in the definition of the derivative of a variable with respect to time. So if time is continuous, we have here the definition of the derivative.
A dot over a variable always denotes the derivative with respect to time, so that's basically defined here. And then we take the difference between two time points of the variable, and we let the time difference between these two time points, delta, become arbitrarily small. So we take the limit as delta goes to 0 of the difference between xt plus delta minus xt. Now, in continuous time, we can make delta arbitrarily small, and in the limit, we basically arrive at the change of the variable at the particular moment t in time. In discrete time, however, delta cannot be made arbitrarily small, because for any delta that is different from 0, the lowest value is 1 that we could get. So in discrete time, the change of the variable between two time periods is xt plus 1 minus xt. So that's the difference operator then. And we cannot take the derivative with respect to time because this definition for the derivative cannot be obtained. Now, with the information that we have at our disposal, we can calculate the growth rate of a variable in discrete time and in continuous time. And we denote the growth rate of a variable x, henceforth by gamma sub x in this lecture. So in continuous time, the growth rate is then given as the derivative of the variable with respect to time, that is the change in the variable at a particular moment, divided by the level of the variable at that particular point in time. So that's basically the percentage change of this variable. And in discrete time, we know the formula for the growth rate very well. We have the change in the variable between two time periods divided by the level of the variable at the beginning period xt. And now you see here that these two definitions are analogous to each other. So we have in the numerator the change of the variable, here in continuous time and here in discrete time, and we divide by the level of the variable in the denominator to get the growth rate. So we have the growth rate in continuous time and the definition of the growth rate in discrete time. And these two are basically approximations to some extent. So if time is indeed continuous, then the true growth rate would always be the derivative of the variable with respect to time divided by the variable itself. So the growth rate in continuous time. But if we only measure this variable in discrete time, then we can approximate the continuous growth rate by the discrete growth rate and by making the time changes arbitrarily small. So basically this is an approximation, and the approximation becomes better the closer the growth rate itself is to 0 and the smaller the time step is between time t and time t plus 1. For example, if you calculate the growth rate of a weekly data series, then the approximation is typically rather good. Also for quarterly data, the approximation is rather good, and even for yearly data, it's usually not a big problem to take the discrete time growth rate instead of the continuous time growth rate, so the two would be rather similar as long as the growth rate itself is not very high. But, for example, you know that we also deal with overlapping generations models, where one time step is not 1 year, but one generation, so typically between 20 and 30 years. And in this case, the approximation error that you can make would become rather high already. So basically what we take from here is the definition of the growth rate in continuous time and in discrete time, and that the two are rather similar as long as the growth rate itself is low and the time step between two variables is low. But if the growth rate is high, or the time period that passes between time t and t plus 1, if that is long, then the approximation gets worse. Now, if a variable grows at a constant rate over time, then it's said to grow exponentially. So for the growth rates that we had on the previous slide, in continuous time and in discrete time, we can basically calculate the level of the variable x, either in continuous time or in discrete time, at any point in time when we know the initial level of the variable. And basically, as we will see later on, this is the simplest formulation of a differential equation, and this is the simplest formulation of a difference equation. And the level of the variable at time t is basically the solution of this differential equation. If we take the particular starting value, then we get the particular solution of the differential equation. So with a growth rate gamma x in continuous time and an initial level of the variable x0 given as x sub 0, then we can calculate the level of the variable x at each point in time by taking the initial level and multiply it with the growth factor being e to the power of the growth rate times t. So for any point in time, we basically know then the particular level that the variable x attains. And we can do the same for discrete time. So we know the growth rate of the variable, we know the initial level. So the variable at time t is the initial variable at the level of the variable multiplied by the growth factor. But the growth factor in discrete time is 1 plus the growth rate to the power of t. And in continuous time, it's e to the power of gamma x times t. So that's the difference between these two solutions. As we will see later, this is the particular solution of the differential equation in continuous time and of the difference equation in discrete time. And if we do not know the initial level of the variable, then we get the general solution, that is basically all solution paths that are consistent with all different initial values of the variable. So there are infinitely many general solutions of differential equations and difference equations, but only one particular solution that belongs to one particular starting value. In fact, it does not need to be the starting value, but only one value along any of the different time points where we pin down a particular value of the variable, and then we can solve for the particular solution, which is one solution path that is selected out of the infinitely many general solution paths by pinning down one variable at one point in time. But we will talk about this later. Now, what we see if we look at the first line, continuous time, is that we can use a simplification for calculating the growth rate actually in continuous time. And this is kind of a shortcut that often comes in handy. And that is that the growth rate of a variable in continuous time can also be calculated. So it can be calculated according to the definition that we had on the previous slides by taking the derivative of the variable x with respect to time and dividing by the level of the variable. But this is sometimes rather difficult or cumbersome calculation. But an equivalent calculation is that we take the logarithm of the variable itself first and then differentiate the result with respect to time. And you can see this easily if you take the logarithm of this expression. Then what we have is the logarithm of x0 times gamma x times t times the logarithm of e. The logarithm of e is 1, so what remains is gamma x times t, and if you take the derivative with respect to time, what remains is gamma x, the growth rate. Another possibility to arrive at this result is by using the chain rule, basically. If you take the chain rule and you look what the derivative of the logarithm of a variable with respect to time is, then you know, if you take the logarithm of a variable, what you have is 1 over the variable itself, so that's 1 over xt, and you have to take the inner derivative of xt with respect to t, and that's the derivative of x with respect to time. So we also get to this expression. So that's important. The takeaway is that we can often simplify the calculation of the growth rate by taking the logarithm of a variable first and then differentiating with respect to time. Now we have seen on the previous slide the solution of a differential equation, and here I show you how you arrive at this solution. That was basically the simplest case. It was a homogeneous linear first order differential equation with constant coefficient that can be written in the form that the derivative of the variable with respect to time is equal to a constant times the variable itself. And that's basically what we had on the previous slide when we had the growth rate of the variable. as given by gamma x, and gamma x is just substituted by g here. So basically that was the expression of a homogeneous linear first order differential equation with constant coefficient. Now, how do we solve it and how do we arrive at basically this equation here, this particular solution? And we also will talk about the general solution. Well, the first step is we bring this differential equation to the form that we had on the previous slide. So we have the growth rate here, and that's the constant. And we obtain this just by dividing this expression by xt. Now, the next step is, since we want to solve the differential equation, we actually want to get rid of the time derivative. So we want to find an expression of this variable where the time derivative does not show up. Now, therefore, we take the inverse of the derivative, and that's taking the integral. So we take the integral on the left-hand side of this expression here, and we take the integral on the right-hand side of this expression here. Now, when we take the integral, we know the integral of a constant with respect to time is the constant multiplied by time, and we have the integrational constant that we denote by C1 here on the right-hand side. And on the left-hand side, we have the integration of x dot over x. But now we already know from this expression here that the integral of that must be equal to the logarithm of x, because the integral is the inverse basically of differentiating. So we get here the logarithm of x times t plus the integrational constant that we denote by c0 on the left-hand side. So c0 and c1 are arbitrary constants of. Now what we still don't like on the left-hand side is basically that the logarithm shows up, and we want to get rid of the logarithm to have a better expression. So we exponentiate the whole result from the previous slide. And exponentiating means we have e to the power of the logarithm of xt plus the integrational constant on the left-hand side, and we have e to the power of gt plus the integrational constant from the right-hand side. Now, e to the power of the logarithm of something is the something itself, so that what is written inside the logarithm on the left-hand side. And we bring e to the power of c0 to the right-hand side here to collect it with the constant of integration on the right-hand side. So basically what we have is that we divide by e to the power of c0 and bring it to the right-hand side, and that's the same as having e to the power of c1 minus c0 on the right-hand side. And then we get this expression here where on the left-hand side we isolated x as of time t, and on the right-hand side we have e to the power of gt times the constant of integration c, that is basically given as e to the power of c1 minus c0, which results from bringing e to the power of c0 to the right-hand side. Now this, as I said before, is the general solution of the differential equation. And the general solution is basically there are infinitely many solution paths that fulfill this general solution, because c can attain any value. It's an arbitrary constant. So we have here the form of all solution paths to which the variable would have to adhere such that it is a solution path to the differential equation that we had initially, to this equation here. Otherwise it could not be a solution path that fulfills this definition for the evolution of the variable over time. However, and this is important, usually we are interested not only in how the general solution path looks like, but in one particular solution path that fits to an initial value or an endpoint value condition, or in fact to pin down any value of the variable at any point in time. Here we do this with an initial value, so we assume that the initial value x0 is given by x sub 0. And then we plug this into this expression here for the time point being 0. So we plug in t0 for time 0, and we plug in for xt x0, and then we solve this equation for the integrational constant. And in this particular case, for this particular initial level of x, we obtain that the integrational constant is x0. So we plug this in the general solution and get the particular solution of the differential equation, and that's xt is equal to the initial level x0 multiplied by the growth factor e to the power of gt. Now this initial level, as I said, selects out of the infinitely many solution paths here the one unique solution path that fulfills the initial condition x0 is x sub 0 at time 0. And then we have the particular solution of the differential equation, and that's basically the same as what you see here when we talked about basically the growth rate and the variable x at time t when we apply this growth rate and the particular initial condition. So this basically shows that we did the calculations right at the beginning, and it shows how you can calculate the general solution and the particular solution of a differential equation. Now in this case, g is the growth rate of x, which we denoted by gamma x previously. And what's just important to note is that there are different conventions in the literature to denote growth rates. I think Barrow and Salah-Martin usually use gamma, others often use g sub x and not gamma x sub x, but yeah, that's just due to the different conventions in the literature. And so what we could have here is that we have both conventions in the slides, because I usually follow the ones in the particular book that I base the model description upon. So be aware that the growth rate could be denoted by gamma x or by g sub x of a different variable. Now we can do the same, the solution for difference equations. So we solve here for this, again, the simplest case, a homogeneous linear first order difference equation with constant coefficient, and that's the same equation that we had previously, where x sub t plus 1 is equal to b x sub t. And now we want to solve this for the general solution and for the particular solution. And actually in this case the solution is even easier than in continuous time, because we can get to the solution by successive iteration. We don't need to take integrals or derivatives or logarithms here. And the reason is again that the variable is not defined in continuous time, so therefore the integral would not be defined over time. Now successive iteration is that we take the first value x sub 1, which according to this equation would be b times x0 if this equation is fulfilled. And so we can calculate every value for x for any given point in time. So for example, for time period 2 we would have x sub 2, which is b times x sub 1, again according to the definition of this equation here. And then we just plug in x1 from here. That means we have b times x0, so we have b times x0, so that's b squared of x0, and so on and so forth for each point in time. And in the end, at the x sub t plus 1, we would arrive at b to the power of t plus 1 times x0, and that would be the general solution of the homogeneous linear first order difference equation with constant coefficient. And again, there are infinitely many general solutions, because we did not yet pin down the initial condition. But again, we can use such an initial condition, and the particular solution follows immediately here. So whatever value we attach to x sub 0, then we would have xt plus 1 is b to the power of t plus 1 times the particular value that we attach to x0. So we can easily calculate the general solution and the particular solution for this case. Now here the growth factor is b. It's again defined as 1 plus the growth rate, as in the previous case that we had here, where the growth factor was 1 plus gamma x to the power of t.
So this was a brief overview of differential equations and difference equations, and how to solve the simplest forms of these equations actually. Why do we need this? Now we will discuss in the next two parts dynamic optimization in discrete and in continuous time. And as we will see, the side constraint in these optimization problems are typically posed in terms of difference equations in discrete time and differential equations in continuous time. And in economic problems, the side constraint is typically a dynamic budget constraint that describes the evolution of assets depending on the choice variable of households, which is typically consumption expenditure. So if you consume a lot, you run down your assets, which is a predetermined state variable. And if you consume less, it might be possible to accumulate assets. Now, depending on this side constraint and the objective function, if you carry out the maximization problem, the result is again a dynamic equation, again a difference equation in discrete time and a differential equation in continuous time. And we will see later on that this is the consumption-Euler equation. And together with the dynamic budget constraint, the consumption-Euler equation now forms a system of two differential equations in continuous time or difference equations in discrete time. And this system again has a particular solution and a general solution. Now, in contrast to what we've discussed before in the preliminaries, we would now need two additional conditions to solve for the particular solution, so to pin down one unique solution path. So one could have, for example, two initial conditions, one on consumption and one on assets, but typically what we would have in these types of constellations is that consumption is a choice variable that can jump at each moment in time, and only assets or the capital stock is a predetermined variable. So what we will typically encounter in these type of problems is an initial condition on the capital stock, so where the system starts, and an endpoint condition where the system ends, also on the capital stock. And these two conditions then allow us to pin down the unique optimal consumption path over time, for example, in the Ramsey-Cass-Koopmans model that we will have a look at later on. And this endpoint condition has a name, and this is the transversality condition, as we will see later on.